Hey guys, so as part of my course, Biological Psychology, I have to present an oral presentation, and the oral presentation I'm presenting today is Describe one biological theory of appetite regulation. So the theory that I'm going to be mainly looking at today is of the glucostatic theory of hunger, and I'll also be touching slightly upon the lipostatic theory. So to start us off, we're going to be looking at the background of the glucostatic theory. And it begins with this man, Antoine Carlson, and he's a Swedish physiologist, and he plays forward this idea that changes in our blood glucose level serve as signals for meal initiation and termination. So what do I mean by this? So when you feel hungry, your blood glucose levels are low, and when you feel full and not hungry, your glucose levels are high. So this is the idea that Antoine Carlson plays forward. So now we come to the architect of the glucostatic theory, and we come to Jean Mayer. And in the 1950s, he plays forward this idea of a glucostatic theory. So what is this glucostatic theory? So Jean Mayer builds upon the work of Antoine Carlson by proposing this idea that certain regions within the brain can actually detect the decreased levels of glucose within the blood, and this leads to the perception and expression of hunger. And those two words, perception and expression, are key, and we'll come back to them later. But specifically, Jean proposes this idea that key hypothalamic neurons can actually detect a rise in our glucose levels, and this leads to the physiological response for meal termination, so feeling full. And I try to represent this by the graph at the bottom here. This red line at the bottom represents our glucose levels, and the blue line represents our hunger levels. So when our glucose levels are low, we're feeling really hungry, and vice versa. You might be wondering, where does this lipostatic theory come in? And if we go back to this glucostatic theory, May argues that this is responsible for our short-term control of hunger and food intake. And he argues that a lipostatic mechanism is actually responsible for our long-term regulation of body weight and energy. So May argues that this lipostatic mechanism is responsible for our long-term regulation of body weight and energy. But how does that actually work? So this lipostatic theory argues that certain regions within the brain can detect our levels of free fatty acids. And so very similar to the glucostatic theory and how that it monitors our glucose levels. So I've got two scenarios right here. The first scenario is that we have high levels of free fatty acids within our blood supply. And if there's high levels, that means there's an increase in our feeling of hunger. Because if there's a lot of free fatty acids, that means that there has been a breakdown of fat. And if there has been a breakdown of fat, that means our body needs to compensate for that breakdown by eating more and gaining that fat back. And the other scenario I've got here is low levels of free fatty acids. So if we've got low levels, we've got a low feeling of hunger. We're not feeling that hungry. And that's because not that much fat has been broken down, and not that much fat needs to be replaced by eating. So hopefully that makes sense. Now that we have looked at the foundation of the glucostatic and lipostatic theory of hunger, we're going to be looking at some peer-reviewed articles to try and gain a deeper understanding about how these theories can hold up in the modern day. The first article we'll be looking at today is by John Speakman, and he investigates the lipostatic theory of hunger. Within this article, Speakman argues that there's a multitude of problems with the lipostatic theory. Firstly, he argues that the molecular basis of the lipostatic set point system has never been discovered. Then secondly, he takes the approach of the evolutionary perspective, where he argues that if humans had a lipostatic set point system, then on average you would regulate fatness with a tolerance of 4%. And if we take that 4% as the truth, that means our body would be regulating in a manner that maximizes our fitness between 1.6 and 7% of the time. Continuing on from the last slide, if our body is regulating in a manner that maximizes our fitness between 1.6 and 7% of the time, Speakman argues that this means that over 90% of our time, our body is regulating in a manner that is adverse for our fitness. And if we go back to this evolutionary perspective, Speakman argues that if we have a system that 90% of the time is adverse to our fitness, then it wouldn't evolve by natural selection. Alternatively, Speakman argues for the settling point and dual intervention point models, but this presentation doesn't intend to investigate those two models. The next article we'll be looking at is by Chaput and Tremblay, and they look at the glucostatic theory in terms of the risk of obesity and diabetes. This experiment contained two studies. The first study looked at the association between the glucose levels in the bloodstream and the changes in body mass, and this was monitored over a period of 6 years. The second study looked at the association between glucose levels at the end of a weight loss program and if there was weight regain following the weight loss program. One of the key findings of the Chaput and Tremblay study is that they found a correlation between the disruption in blood glucose levels and an increased risk of obesity and diabetes, although they did find some mitigating and aggravating factors. One mitigating factor is of regular exercise. So regular exercise is actually correlated with an improved accuracy of blood glucose regulation. And then some aggravating factors is of rapid fat loss and of short sleep, so not getting those 8 hours of sleep. To summarize this article, the work of Chaput and Tremblay actually support the work of G. Mayer, as they found low levels of glucose was correlated with weight gain and weight regain after weight loss. And it was also linked with short sleep duration, so not getting those 8 hours of sleep. The last article we'll be looking at today looks at the glucostatic theory in terms of a buffet. Specifically, this article intends to investigate the self-reported levels of hunger and fullness following the administration of the buffet, and whether there's a correlation with the amount of glucose that is consumed. Secondly, whether or not the glucostatic theory is a primary predictor of how long a person stays full. And then lastly, whether or not the glucostatic theory is a primary predictor in how much food is consumed. This article found support that the glucostatic theory was able to predict self-reported levels of hunger and fullness, although the glucostatic theory was not a primary predictor in how long a person stays full or how much food is consumed in a buffet type setting. So, to summarize what we've looked at today, we've covered the background of the glucostatic theory of hunger, what constitutes the glucostatic theory, how the lipostatic theory fits into the picture, and then lastly, we ended with some peer-reviewed articles to gauge the evidence for these theories. These are the articles I used throughout the presentation, and thanks for listening.